Today we're going to do a computer simulation of a two-dimensional collision in an attempt to verify the law of conservation of momentum in two dimensions, both x, y, and then of course the resultant momentum as well. You're going to go to Google Classroom, you're going to see a title Two-Dimensional Collision Lab. You're going to open it and you're going to see three things there. One is some instructions. If we click on the instructions, it outlines exactly what you have to do for this. Then, after we've opened up the instructions, read the instructions, and know what we have to do, we're going to literally open up the applet. Click on the link below that in order to open up the applet. You're going to see in the instructions that when you open up the applet, you're going to first click the Advanced tab, not Introduction. That's going to be the default Introduction. That provides us with a one-dimensional collision, but we don't need to do that because we've already done a lab as a one-dimensional collision. So we want to look at the Advanced, which is a two-dimensional collision. There's also a couple settings that we have to change in here, again, outlined in the instructions that I've printed for you. The first thing is to go over to the right-hand side in this green box over here and uncheck the box that says reflecting border. What that does is allows these objects, once they hit each other, to go off into the farther reaches of space. They never bounce off the borders. If I have that reflecting border in there, still checked off, they collide with each other, they're going to end up bouncing off the borders around the edges, and we don't want that, okay? So we're going to uncheck that box so that those reflecting borders aren't there. The second thing we're going to do here for settings is click this little box that says More Data. We don't just want the mass and position, we want the mass, velocity, and momentum. Now, when you go to actually collide these two objects together, before you do, I want you to change some numbers. Okay, I want you to change the masses. They've got it 0.5 kilograms and 1.5 kilograms as the default. Change one of them. Change both of them, whatever. All I'm saying is that I don't want those two masses. I want at least one of them a different mass. I don't want anything the defaults, all right? Now, in addition to that, you can change the position of these objects literally by just clicking it and dragging it. You can change the direction of the velocity by clicking that and dragging it. You can change the magnitude of the velocity or the speed by clicking it and dragging it. Change everything. Change everything around. The mass, the initial velocity, the initial position, and so on. Change everything. Just make sure that it's set up so that when you press the play button, they're going to collide with each other. Okay, this one isn't going to work very well because when they, actually this one would work because they ended up colliding. I didn't think it was going to collide. Okay, we want to make sure that when we do this, they collide. If you happen to set it up and they don't collide, all right, not the end of the world, just do another trial where they do collide. Does that make sense? All right, so what data do you have to collect and what do you end up, and how do you end up collecting it? Let's restart that. Since that worked out, we'll just leave these numbers there. We'd record on a table that appears also as an attachment in your lab right here. We would record in these tables that are in this lab, we would record the masses, in this case 0.5 kilograms and 1.5 kilograms. We would press play, stop it before they hit each other, record the velocities, the x velocity, the y velocity, both initial and final, and the momentum, x and y, initial and final. Then we would press play again, restart it. After the collision, pause it, record the values of the x and y velocity, final. Record the values of the x and y momentum, final. Again, on the tables that we saw on that document that's already created for you. Make sense? Now, once you have that data, you're going to do some analysis with it, and then you're going to repeat this. Do another trial. Change the masses again. Change the positions again. Change the initial velocities, directions, the magnitudes of the initial velocities, and so on, so that you have the same thing as we just did, but with different data. Make sense? All right, let me take you to that template. Good news is, this is not a full lab write-up by any stretch of the imagination. In fact, all you need to do is what's included in the template for you already. You don't need to write out a problem. You don't need to write out a conclusion. You just need to fill in the table, fill in the blanks, and then answer the questions that are listed there. So let's say that I recorded my data for trial number 1, and I saw that my initial velocity, x component, for ball number 1 was, let's say, 5. Okay, my initial velocity, x component, or horizontal component for ball number 2, was 2. That gives me, and I would have to calculate this by hand, a total initial momentum x component of 7. Sorry, not a total initial momentum, but total initial velocity, right? Then I would do the same thing for the final, and for the initial and the final for the vertical. Let's say I've got 4 right here. Let's say I've got 1 right here. That gives me a final velocity of 5. Make sense? Then I would do the same thing for the vertical velocity. Let's say I've got 6. Then I've got -2. Okay, those add up to give me 4. And then I would do the same thing for the final for the vertical velocity. Let's say I've got 5. And let's say I've got 1. That gives me a total of 6. Now, down below that, you see 2 boxes where you have to draw vector diagrams. The vector diagrams are meant to resolve the vectors, to combine the vectors for x and y components. Here's how you're going to draw those vector diagrams. Now, pay close attention. Each of these vector diagrams will be right-angled triangles. Got it? They will always be, for all of them that you have to draw in this activity, right-angled triangles. The vector diagram for the initial velocity, I have an initial horizontal of 7, an initial vertical of +4. Do you see that? Initial horizontal of 7, initial vertical of 4. So what I want to do right now is draw a diagram with a 7 to the right and a 4 upwards. I'm going to click Insert, Drawing. Then I'm going to click on Select Line, select an arrow. I'm going to draw 7 to the right. And I'm going to draw 4 upwards, roughly to scale, as best as you can to scale. And then I'm going to draw my resultant vector, which is always, of course, drawn from start to finish. My resultant vector is going to go right here, from start to finish. And I'm going to change the color of that to red or something else so that it's distinguished from my component vectors. Make sense? So I've got 7 right here, I've got 4 right here, and then I've got my resultant right here. You can label, in fact, you should label, using a text box, this as 7 meters per second. Label this one as, with a text box, as 4 meters per second. And then label the resultant. You're going to have to calculate that, right? How are we going to do that? 7 squared plus 4 squared, square root that, and you're going to get the resultant there. I didn't actually calculate that, so I'm not sure what that is. You would fill that in once you calculated the value. Click Save and Close, and then that's automatically going to appear in your box there. Make sense? Do the same thing for the y component, or sorry, for the final velocity, I should say. X component and y component, see what you get, and then answer the 3 questions that go along with that. Still within trial 1, you're going to do effectively the same thing, but with your momentum vectors as opposed to your velocity vectors. All right? And then, of course, if you scroll down further, you're going to see trial number 2, same thing, velocity vectors and momentum vectors. So there's 4 tables. There are 4 sets of vector diagrams that you have to draw, but they go pretty quick once you get the hang of it. And then there are 4 sets of questions that you have to answer. There's not really any justification that you have to provide for these. It says, is the x component of velocity conserved in the collision? Well, the answer is either yes or no. If the x component was 7 before the collision, and the x component afterwards was 5, was velocity conserved in the x component? No. Okay, was it conserved in the y component here? Initial is 4, final is 6? No. At least according to the data that I've cooked up for you right there. Okay, and then, of course, the final question there is the resultant velocity conserved in the collision? You're going to tell that by your resultant vector that you plotted for initial and final.